Hello everyone, and welcome to this new lecture. And we will quickly start without wasting any time. What we were doing is the scattering in the central force field, and basically we discussed some part of this and some nomenclature which were related to the scattering process. So let us quickly review that we are actually doing this a two-body problem is there, like you have an alpha particle is going to be scattered with some target, like in Rutherford scattering. Later stage we are going to discuss the later stage Rutherford scattering, and what we are assuming that the project particle in the projectile, these are all of equal mass, and uh, incident energy are going to be equal when they are moving towards the center of the force. And second assumption was that assuming that the force between the incident particle, what is going towards the target, and the center of the force is false of zero at the last distance. That is the force which is acting between the target, what is your target, where this projectile is going to hit, is 1 by r square. So that as the distance increases between this target particle and this projectile, that the force effect of the force is going to be zero at large distance. And because of this, that if you have a particle of positive charge and your target is of positive charge, then if they are going towards it with certain energy, that it will deflect it from this because of the Coulomb repulsion, then that will go, it will change its path, and it will go towards some other thing, some other scattered direction. And as it will go further and further, its path will be then again a straight line, but not in the direction of the initial one. Okay. And it will define the intensity of the incident beam, that is I naught, is called the number of particles passing through the perpendicular area per unit time per unit area. That is what you have, the number of particle crossing per unit area per unit time normal to the beam. Okay, so if you have an area normal to the beam, so if this beam is coming and I have area normal to the beam, not area not like this, not like this, but if the beam is coming and this area is perpendicular, then how much number of particles is going to hit it and passing through this perpendicular area per unit time. This is the intensity or the incident flux. Okay. Then that is that I already discussed, that after passing the center of the force, the particle goes away as scattered, and it is going to have its straight line path, not initially in the direction of this. And this process is known as the scattering, or the particle is said to be scattered from its initial direction. And then we discuss this scattering cross section, and that scattering cross section is we had discussed that this is going to be the number of particles scattered into solid angle d omega per unit time divided by the incident flux. And then if I integrate over this solid angle, then it's going to give me this total interaction cross section, which is important quantity. Third thing is scattering angle. So that is the angle between the incident and scattered direction. So this, if the particle is coming here, so this particle is coming, and then if it is like it is going in this direction. So this is my force. So there is no angle between this direction and this. So but if because of this force, these particles get scattered from its original path, then if you draw a asymptotic from here, then the angle made by this is say theta, or this angle, this is theta, is going to be known as the scattered angle. Okay, so this is scattering angle. And then there is the impact parameter. Impact parameter is what is if you draw a perpendicular from this, if you have a line of force from the force center, if you draw a perpendicular to the line of the projectile, the velocity direction of the particle, then this is going to be the impact parameter. For example, this is the velocity direction of the particle here. So if the impact parameter in this case is, you have to draw the perpendicular. So this is going to be the impact parameter. Now draw a perpendicular to the direction of the incident particle from the scattering center, then the height of this perpendicular is known as the impact parameter. That is, this is what you have. So then we discussed about this because the force is central, so there must be a complete symmetry about the axis. So this is my axis, this is my x, and this is my x prime. This is my axis which is passing through this force center. So if the force is central, there must be complete symmetry about this axis on the incident beam. That means the beam is coming, that the reflecting the beam is coming from all the direction, and then the reflection could be in all the directions. So you have a symmetry around this axis. Okay, so that's why there is a solid angle is in this case is twice pi sine theta d theta, because you can make a solid sphere about this around the center. You can make a solid sphere around the center, and then you can define the solid angle, because from where this scattering is taking place. So I think that you know what is solid angle, and why this is twice pi sine theta. So I can, okay, so here you can say that solid angle is nothing but, because you define solid angle d omega is this is dA upon r square. dA is area. So this is or this is going to be our, if solid angle is like area and then r square. So area of a solid sphere is going to be 4 pi r square, okay, divided by r square. So that is, solid angle is going to be 4 pi. So that is and in this case, if element of the solid angle if you consider, so if you consider for example, if you consider a part of the sphere is like kind of this is say x, y, and z axis. So this 4 pi square is the total area of the solid sphere. So if I take one small component of this of the solid angle, which this is about d omega, because this dA, I'm talking about this area dA. So this is my angle theta, and if I project this is on this axis, so I'm going to have this line also, this line. So this angle is my phi, and this angle is my d phi. So for this area I need this length and this length. Okay, so this length is like is projected here, is this is the arc of this. So this is going to be this length multiplied by this d phi. So this length is nothing but equivalent to if you see that this is, if you draw this is the radius of this is r. So this is going to be r sine theta. Okay, r sine theta. Okay, and then this r sine theta multiplied by this d phi is going to be multiplied by d phi is going to be this length. Okay, this. And what about this length is nothing but what, this is r and this is d theta. So this is going to be r d theta. So this area is this multiplied by this. Okay, so this one multiplied by this. So total area is length plus breadth on in this case, and this one length is r d theta and this is r sin phi. So if you multiply dA is here is r d theta and then r sin theta d phi. So if I integrate this dA is going to be, this is r square. You integrate theta sin theta d theta is from 0 to pi, and this is phi is from 0 to 2 pi d phi. So d phi is going to be twice pi. So this is going to be twice pi r sin theta. R is twice pi r square sin theta d theta, or you write twice pi r sin theta d theta. Okay, so this is why you write twice pi r sin theta and r theta. Okay, so divided by r square is the solid angle is giving you by twice pi sin theta and d theta. Okay, so this is all the particles are coming. These are the direction of the particle which are coming. Projectile which is having same mass and energy, they are facing a perpendicular target of this area d sigma. The area of this is like say in this case is going to be twice pi s. S is the radius of this circle, and the thickness of this circular disk is going to be ds. So that's why this area is twice pi ds. And then when this is a scattering center, and from the scattering center they got scattered. Okay, that it is shown here, they are getting scattered. And if you draw a swarm toad from there, from these scattering, so these will give you the angle of a scattering. From this to this is going to be a small deviation d theta. Okay, so these are going to be the angle of a scattering, you can see here and here. So when these are going to have a solid angle here, d omega. Okay, this is going to be d omega. This is what is going to be twice pi sine theta d theta. So whatever the number of the particle which is scattering through this perpendicular area, they are going to be scattered through a solid angle 2 pi sine theta and d theta. So this is what here is written, and there is a symmetry, that's why this is going to be along x axis. So this we have that crossing through the incident particle crossing through d sigma area, that is this d sigma area. This is s, and this is my ds. Okay, so twice pi s ds. So then this is incident particle crossing through d sigma. D sigma is this. So we know that these particles are scattered into the solid angle, which is d omega, and we have calculated is twice pi sine theta d theta. And also I know that this I omega is I naught d sigma, because I naught is the incident intensity. Okay, and is giving me the number of particles scattered, and I is the number of scattered particle, intensity of the scattered particle. So that's why number of particle which are incident particle, which is scattered in the direction of this omega per unit solid angle, is basically the intensity of the scattered particle. So hence the number of particles scattered into the solid angle d omega r. So this is per unit solid angle, this is per unit solid angle. Then so what is the number of through that solid angle is, because if you multiply it by d omega, then this is per unit solid angle, and then if you multiply it by the total element of the solid angle, that is d omega. So this is going to give you the number of particles scattered into the solid angle d omega. And I know that this I is from here is in terms of the incident flux, I naught d sigma and d sigma. So this is equal to I naught, and this d omega, this is d omega is twice pi sine theta d theta, twice pi sine theta d theta, and you know that I naught sigma omega is here. So now I can use okay, so here I have written this one thing, that it's same. This is I naught is the incident, and this is the particle which are crossing through. So this is going to be I naught twice by s ds. This is nothing new. So now with this I can have this is what equal to if you consider this number, this is I omega d omega is I naught d sigma. Okay, I naught d sigma, if you remember this. So this is I naught d sigma, this is I naught I naught d sigma, this one. Okay, so I naught d sigma, I'm going to put I naught twice pi s ds equal to this whole thing. So twice pi I naught d sigma ds is twice pi sigma I naught sine theta d theta. So here if this is under mod is taken care to negative and positive, because s and theta are related, because as the s increases, that is s is the impact parameter, as this is the line of the angular force. As the particle is coming at this direction, then deflection will be more, because the theta will be more, and then it is going to the impact parameter is large, that is the perpendicular distance from this force is, so then it's going to less deflected. So that angle is related to s and this angle scattering are related. Okay, so if the particle is like coming, this is my scattering force center, so if a particle coming close to this, so that is going to deflect more, because then impact parameter is less, theta is more. And if a particle going is very high, this is impact parameter is high, then this is going to deflect less. Okay, so then the scattering angle is going to be this, and scattering angle is going to be this. So depending upon what is the impact parameter, the theta is going to change. It's going to be, so that's why this is mod is here with the negative absolute value of sine. And again, I can have the impact parameter depends upon theta and E, because I can write impact form in terms of theta E. So from this relation, I can find this d sigma. This is scattering differential scattering cross section is because 2 pi will cancel out and I naught. So I just have is s upon sine theta, and this d sigma by ds by d theta. This is scattering differential scattering cross section. Now we will try to calculate it in what in Rutherford scattering. Okay, so before that, we are going to write a formal expression for the scattering angle theta as a function of the impact parameter, as because this can be written in terms of this, or then if you write s in terms of theta, you can write theta in terms of s also. Okay, so this is what we're going to write. So because we know that in central force potential field, that two body potential two body interaction reduced to one body interactions, so we have the theta is expression, if you remember, this is in terms of this. So as the orbit because the orbit is going to be symmetric about the direction of the periapsis, that is periapsis is basically, if this is my force center, periapsis is the closest approach from the incident direction. So periapsis is the scattering angle is given as theta equal to pi minus 2 pi. So because this is my periapsis, so the particle is coming and then it is getting deflected at this position. Then if you draw perpendicular to this, so closest approach, the closest to the center is this, and then this is making an angle. This is making an angle. This is my scattering angle theta, and then this is making angle psi. Okay, so because this has to be symmetric around the periapsis, so that's why if this angle is psi and this angle has to be equal to psi. This is Rm. This is the approach, the closest approach. Okay, so then you can see that theta is pi minus, total angle is pi minus 2 psi. So where psi is the angle between the direction of the incoming asymptote, this is the incoming asymptote, and the periapsis, the distance of the closest approach, this is your psi. Okay, and because if you forget this, this is not there, because around this scattering has to be symmetric, then this angle has to be also equal to psi. Okay, so that is what the argument is. So now in this expression, if I take my theta 0 to be pi, because if r naught, the particle is coming from the infinity, so this is r naught is infinity, is coming from infinity, and theta naught is pi, that is the from incoming direction, that is there is no deflection, so angle is pi. So this is angle is pi. So when theta, so then if deflected, then theta naught becomes this pi minus psi. So when this r is Rm. Okay, so when this if you see that when this is center of force, when this is Rm, so that theta naught becomes this pi minus psi. Okay, because earlier it is going to this, and then it is psi. If you subtract psi angle from this is going to be pi minus psi. Earlier it was if it's going like this, coming from r naught to infinity, and then it's going like this, so it's going to be pi, and then it's going deflected, okay, making an angle psi, that this is going to be pi minus psi at r equal to Rm. So I'm going to put this pi, okay, and this is the limit is from infinity to Rm, and then this becomes pi minus psi, and for this angle pi, so for this pi, this is going to be pi minus psi. Okay, so and what I do is this is if I take this will cancel out, and I have minus psi, so psi will become psi. You get this integration gets reversed from Rm to infinity. Okay, and nothing else. And then what is this has been used. So for any given particle, the constant of orbit and hence the amount of scattering are determined by its energy and angular momentum. Okay, so if you know that the angular momentum conservation is that L is equal to m naught s, because you know angular momentum L is rp. Okay, r in this case is my s and p is m, and this is v naught is the relative velocity v naught. So this is going to mv s, and energy is half m naught v square. So if from energy is from v naught is going to be twice E by m from this relation. So if I put v naught here at this place, so Sm and v naught is under root twice E by m. So this S is S, I can write under root m, and this is twice E by m. So this becomes S. Okay, so 1 under root m, 1 under root m cancel out. So this is twice E msc. So I'm going to use this in place of twice me. So if I square it, so this is going to be L square equal to S twice me. Okay, or I can write this S equal to twice me by L square. So I'm going to use this S twice me by L square, twice e by L square to equal to S. Okay, okay, S square. So this is because twice me by L, this is 1 by S, because twice me by L square by twice me is S square. So this is 1 by S square. Fine. And then again I want to have is, if I multiply it by E here and divide by E, so this is twice me by L square is going to give me 1 by S square, and then I relate V and E is here itself, and then I have 1 by R square. So if I take 1 by S square common, so this from this I'm going to 1, and this is going to give me Vi by R, and then R square is there. Now I can take this U is equal to 1 by R. So if I take okay, so then 1 by R square is also taken common, 1 by R square. So this is R square and this is minus 1. So if you R square you take outside, this become 1 by R. So this become this will cancel out. So you are going to have just R here. And then if I take 1 by S square also outside, so 1 by S square comes out, this becomes 1 by S, and this S goes up here. So this is you have here, and then this is 1 minus E is there, and then this is going to be S square, because we're taking S square common. Okay, so now what you have the relation that theta equal to this scattering angle is pi minus 2 psi, and then you have psi equal to pi by 2 minus theta by 2. So you can write this psi equal to here you can write psi equal to pi by 2 minus theta by 2 here itself, or then or you can write this twice psi equal to pi minus theta. So you write twice psi equal to pi minus theta. So this is what, and once you get rid of this psi equal to pi minus theta, you write psi equal to pi minus theta 2 psi, and then you write theta equal to, so then this is basically, or you okay, so this is straightforward, so you don't have to do anything, because you write, so if you multiply it by 2, you multiply it by this becomes 2 psi, this is your psi. So theta equal to pi minus 2 psi, this is what you have. Okay, forget about all these. So from this relation you get theta scattering angle in terms of S. Okay, so theta angle in terms of A, you can calculate this parameter. Scattering angle, when you know this S, you know the energy, you know the potential. Okay, and when you know the S, you can find out what is going to be the scattering angle from this. So this is a preliminary all about this scattering, and then if I'm going to apply it on the case of this Rutherford cross section. Okay, so I'll be going to touch this part of Rutherford scattering cross section in my next lecture. So I'll stop here because let's quickly review what we have done here. So today we try to understand what is actually is happening, d omega, omega, and all these things, solid angle, and then we try to calculate this scattering cross section, that is in terms of the parameter s upon sine theta, and we try to calculate also this scattering angle in terms of the impact parameter. Okay, so in Rutherford scattering we're going to use this sigma theta to calculate the Rutherford scattering cross section. Okay, so I think I'll stop here, and then in the next class we will start from this topic, that the Rutherford scattering cross section. Thank you very much.